addition rule. So one of the rules in probability that we use is addition rule. When we add things, we need at least two numbers. Suppose when we say, well, I added this and that, so you actually have two items, this and that. So you need two items to add, or else it wouldn't make any sense. So addition rule is typically used when we have two or more events. We talked about events in the last video. So if we have more than one event, then we will use addition rule to find the probabilities of a combination of events. So compound events are events that consist of more than one event. So if we have more than one event, just like sentences, it could have a simple sentence, or you could have multiple simple sentences combined together to form a compound sentence. And anytime we have compound sentences, there comes the part of speech conjunction to play a role. So we would start saying, I bought a car and I took it for a ride. Either you pick an orange or an apple. So the logical conjunctions that we are interested in are or, and lastly, not. So or is also called as union, and is intersection, and not is the simplest of all, which is the complement. So let us consider two events A and B. And I'm going to define A raised C to be the complement of A. So the probability of A complement will be related to the probability of A. What does the probability of A complement mean? That simply means the probability, going back to the logical statement corresponding to a complement, that would simply mean not A. Anything that is not A. So in the entire sample space, we're going to pick everything that is not A. So the probability of choosing everything from the sample space is 1. I'm going to do an example in a bit. So the probability of choosing an entire sample space is 1. So if I'm going to pick everything that is not A from the sample space, it would simply be 1 minus the probability of choosing the event A. So rolling a 6-sided die, we know the sample space is 1, 2, 3, 4, 5, 6. And if I defined an event probability, getting a number greater than 0 and less than 7. This would mean the possible outcomes for that event is 1, 2, 3, 4, 5, and 6. So for this experiment, I simply chose the entire sample space. So the number of outcomes in the sample space is 6. The total number of outcomes would be 6. So the probability of choosing the entire sample space is 1. Now I could relate it back to what we had here. So if I define event A to be getting an even number, then the elements that would correspond to getting an even number would be 2, 4, and 6, because those are the even numbers in our sample space when we perform a rolling a die experiment. So a complement would simply mean not getting an even number, which simply means we are going to get an odd number, so 1, 3, and 5. So probability of A would be 3 out of 6, which would be 1 over 2. And probability of a complement is 3 out of 6, 1 over 2. And I can also write it as 1 minus the probability of A. It'll give you the same answer. The reason for that is if we have the sample space, 1, 2, and 3 would correspond to a complement. Oh, sorry. Two, 4, and 6 would correspond to a complement. Or did I define it as A? I defined it as A. And 1, 3, and 5 would correspond to everything that is not A. So that would become a complement. So if a complement is everything that is not A, we can see from the sample space, if I put them together, I get the entire sample space back. So 1, 3, 5 is a complement, 2, 4, 6 is A. So if I put them all together, I get 1, 2, 3, 4, 5, 6. So that leads us to saying probability of S is equal to the probability. I'm putting them together, so we would have A union A complement. Think about putting things together. That's why we have union. So we know probability of the sample space is 1. So probability of A union A complement would simply be equal to 1. And once I write the addition rule, we can revisit and split this up and write a different property here. So that is what we call the complementary rule. And if we write it in a different way, we will get complementary rule here also. But once I do the addition rule, I will share how we can go from the last part, which is probability of A union A complement equals 1, to what I wrote up there and highlighted in the top section. So we are going to continue with addition rule, and instead of A complement, we're going to have the event A and the event B. So we might have, you might have heard of Venn diagrams, something that we use in set theory. So suppose we have two events. Okay. So we'll call it event A and event B. And forward. I guess it wouldn't let me shade them together. So let's just do it this way. So we have event A and event B. And you can see that event A and event B are overlapping. Another case would be the case that I just drew earlier, where I have two events A and B B here are not overlapping. So that would result in the entire sample space, which you can put a square around usually, but we don't have to do that. Suppose A and B are two events, and we want to find the probability of A or B. So probability of A union B. So how do we find the probability of A union B in the first case? So you want to look for everything that corresponds to the event A, and you divide it by the total. So if I shade everything that corresponds to event A, I will probably or definitely will shade all of that, because that corresponds to event A. So I could write it as probability of A, because that is the part that corresponds to A. Now we have to select for event B. So I'm going to shade everything corresponding to event B. And I'll get that. So all elements that corresponds to event B and divide by the total, I end up getting the probability of event B. As you might have noticed, that right there, it has an overlap of both colors. So I counted it once when I did for event A, then I counted it again when I did it for event B. So all I did here is I counted it twice in finding the probability of A union B. So I have to take one of those counting away, one of those counts away. So I could write it as minus the probability of that part is common to both A and B. In other words, that is the overlapping part that got counted twice. So we write it as A intersect B. So inverted U simply means intersection. So A and B overlaps. So since I counted the overlapping part twice, I'm going to take away one of the overlapping parts. So what I just wrote here is simply the addition rule. The second case will also be addition rule. So, but a simplified version. So if I have probability of A union B in the non-overlapping case, first I'd have the probability of A, which would simply mean I'm selecting elements corresponding to, it's not working. Selecting everything corresponding to A, then I'm going to select every element corresponding to B. So in finding probability of A union B, I would simply have probability of A plus probability of B. And you can see that there is no overlap between the two. So since there is no overlap, I have nothing to take away because I didn't count it at all. Recall that is the overlapping probability and I took it away because I double counted it. But in the second case, there is no overlap at all. So the last part would simply be 0. So that would simply mean probability of A intersect B is equal to 0, and it is not overlapping. In other words, you can see the two events, the two circles, don't overlap and they are not connected. They are separate. So we can also state A and B here are disjoint events. So if A and B are disjoint events, then the probability of A intersect B will definitely be 0. Going back to probability of A union A complement. So we'll call this as so let's say that is the entire sample space. We call it S. And if I selected the event A, and that's right there, I'll shade it to purple. Everything that is not shaded would become a complement or the not A part, because everything that lies outside of the shaded area would be not A. But the area that is not shaded and the area that is shaded, if you put them together, I get the entire sample space, which would be the entire rectangle. So the sample space is merely a combination of the probability of A and A complement. So we know the probability of the sample space is 1. Now, if we use the addition rule, probability of A union A complement, that would be the probability of A, the first event, plus the probability of A complement, the second event, minus the probability of A intersect A complement. So if I say that something or an element is in the shaded part, I can't say that it is in the unshaded part. If I say that an element is in the unshaded part, I can't say that it is in the shaded part at the same time. So it can only be either in A or in A complement, but not in both of them simultaneously. They can't happen together. So that would simply mean probability of A intersect A complement is 0. If an element is in A, it cannot be in A complement. If it is in A complement, it cannot be in A at the same time. So at the same time is the key word here, which is the probability of A and A complement occurring simultaneously. In other words, at the same time. And that is going to be 0. An easier case to look at would be the die rule example where A was even numbers and A complement was odd numbers. So if I rolled an even number, I can't say that number is also odd. Likewise, if I said I got an odd number, I can't say that the number is also even. At any given time, it could either be part of A or it could be part of A complement, but it cannot be a part of both at the same time. So they cannot occur simultaneously. So the probability of them happening at the same time is the intersection. So A intersect A complement, its probability would be 0. So if we use that, we will have probability of A plus probability of A complement. And we know that is 1 from above. If I rewrote that probability of A complement, I'll move probability of A to the other side, 1 minus probability of A. And that is simply the complementary rule I arrived at earlier, using A and not A. So this is one way of looking at the complementary rule using the addition rule. The concept of events not occurring at the same time are also known as mutually exclusive events. Two events A and B are mutually exclusive if they cannot occur simultaneously. That is, the probability of A and B is 0. As an example, probability of getting an odd number and an even number in a single six-sided die roll. So if I roll a die only once, and if I asked you, well, what is the probability that I get both an odd number and an even number at the same time, that probability is going to be 0. Another example, the probability that a rocket launch is successful and it failed at the same time. That probability is going to be 0. If a rocket launch is fully successful, we can't say it failed. If the rocket launch failed, we can't say it was successful. At any given time, only one of the two events would happen. So the occurrence of one would completely exclude the occurrence of the other. So those two events are mutually exclusive. Mutual here is in the context of saying they are occurring together. Exclusive means if one happens, the other will not happen. So that is the principle of mutually exclusive events. So here we have an example where we have a standard deck of cards, a standard deck would contain 13 hearts, 13 diamonds, 13 clubs, and 13 spades. And each of those 13 would consist of numbers 1 through 10, and king, queen, and jack. And number 1 is considered as an ace. So each of those 13, 1 through 10, and we have king, queen, and jack. So, and A is what we call the ace also. I'm explaining this just in case if you've never played cards before. So we're going to pick one card at random from the deck, and we want to know the probability of randomly selecting a 2 or 3 from a deck of cards. So if I define A as selecting a 2 and B as selecting a 3, what we are finding is the probability of A union B. In other words, probability of A or B. So randomly selecting a 2 or 3 from a deck of cards. And what does the rule suggest? The rule simply suggests that should be equal to the probability of A plus the probability of B minus the probability of A and B. What is the probability of A? In other words, probability of selecting a 2. Each suit has a 2 in it. So there is a 2 of hearts, 2 of diamonds, 2 of clubs, and 2 of spades. So 4 of those 52 cards would result in a 2. So 4 in favor of 2 divided by the total. Probability of B is selecting a 3. So each suit has a 3 in it. So in total, we have 4 out of 52, same as A, minus the probability of A and B occurring at the same time. Well, you're picking only one card, and that one card can't be a 2 and a 3 simultaneously. So that would be 0. A and B are mutually exclusive events. So that would be equal to 8 over 52. We could simplify it and write it as 2 over 13. So the probability is simply 2 over 13. You could write it in terms of decimals also. So here in part B, they want to compute the probability of selecting a 2 or a 3 or a 4 from a deck of cards. So I'm just going to define C to be selecting a 4. And we're trying to find the probability of A union B union C. And keep in mind, selecting A, B, and C so A, B, C, all of them are disjoint. In other words, if you select a 2, you can't say it is a 3 at the same time. If you select a 3, you can't say it is a 2 or a 4 at the same time. So they're all non-overlapping. So we can simply extend the addition rule and write it as probability of A plus the probability of B plus the probability of C. If A, B, and C are not mutually exclusive, in other words, if they are overlapping events, then addition rule is not as simple as this problem when we have more than 2 events. So it is easy, and I can simply add the probabilities because they are mutually exclusive. So we computed probability of A already, it's 4 out of 52. B already, 4 out of 52. C, probability of selecting a 4. There are 4 4s in the deck of cards. So 4 out of 52 again. That would result in 6 out of 13. So part C, running out of space. We want to compute the probability of randomly selecting a 2 or a club from a deck of cards. So I have defined selecting a 2 as event A. I'm going to define event D to be selecting a club. So part C wants to find the probability of A or D. So you either select a 2 or you select a club. So that would be equal to probability of A plus the probability of D minus the probability of A and D according to the addition rule. So the probability of A, we already know, is 2 out of, 1 out of 13. So the probability of selecting a club, write it as 4 out of 52 for now. It'll be easier for us to simplify later. So 4 out of 15, same as 1 out of 13. Probability of D is probability of selecting a club. So if we look at our sample space, there are 13 clubs. So the probability of selecting a club is 13 out of 52. Minus, we have to ask, well, could a single card, be a 2 and a club at the same time? In other words, could you pick a card that is a 2 and a club simultaneously? Absolutely, because every suit has a 2 in it. So there is a 2 of clubs, and it could happen with probability 1 out of 52. There is one card that is both a 2 and a club at the same time. So the events A and D are not mutually exclusive. So if I take the common denominator, and numerator is 4 plus 13 minus 1, that is 16 over 52. The answer would be 4 out of 13. So,
wait.
So we have a game of roulette, and we have 0, 0, 0, and we have numbers 1 through 36, and the odd numbers are in red, even numbers are in black. We don't care about whether they are odd or, we don't have to write them out. So what I'm going to do is I'm just going to say odd numbers and even numbers. And now I'm going to give them colors. So 0 and 0, 0 are green. Odd numbers are red. Even numbers are black. Next, we have a count. So odd numbers, we have 18 of them because we have 36 numbers in total. And even numbers, we would have 18 of them. And lastly, here we simply have 2. So those are the counts. In total, we have 36 items or 36 elements. So part A is the probability of green or red. So that would be the probability of green, I'll just call it G, plus the probability of red, minus the probability of G and R, which means green and red at the same time. Well, if it's just one metal ball that's landing on the slot, it can't be both a green slot and a red slot at the same time. So that is, those two events are disjoint, so we would have 0. Probability of green, we have 2 that favor green, and in total we have 38. So that would be 2 out of 38. Red, we have 18. So 18 out of 38. So, oops. In total, if we add them, find the common denominator, we have 20 out of 38, which would simply be 10 out of 19. Part B, the probability does not land in green. So does not land in green means it is going to land in red or black. So we can make use of the complementary rule, and we could say this is equal to 1 minus the probability of lands in or on green, sorry. So does not land on green is simply the complement of landing on green. So if I call this event A, naturally not a landing on green would be its complement, a complement. So we will have 1 minus, well, what is the probability that it lands on green? Well, 2 out of 38. You could do a common denominator, which will give you 36 over 38, which is simply 18 over 19. So you can either use the complementary rule, or you could directly look at the diagram that we drew and pick out, well, if it's not going to be green, it has to be red and black. So how many would favor red? 18. How many favor black? 18. In total, 36 out of 38. So either way would work, but I just wanted to do this problem using complementary rule. So here we have a probability model that shows family structure, and it's a family structure among families with at least one child younger than 18 years of age in 2013. So we have 2 married parents, first marriage, 2 married parents, 1 or both remarried, single parent, no parent at home. Those are the 4 cases we analyze. And if you recall from the last video, this is simply a relative frequency distribution. And we know a relative frequency distribution is nothing but a probability model. I made a reference to this in the last video. So a probability model is pretty much a relative frequency distribution. But we know something about a relative frequency distribution. If you add all the relative frequencies, it must sum to 1. If it doesn't, then it is not a proper relative frequency distribution. If something cannot be a proper relative frequency distribution, it cannot be a probability model. But in this case, if I add all the probabilities over here, on the right-hand side, they will sum to 1. So yes, because 0.46 plus 0.15 plus 0.34 plus 0.05 is equal to 1. Now we want to find the probability that a randomly selected family with at least one child younger than 18 years of age in 2013 had 2 married parents in their first marriage. So out of the 4 levels, 2 married parents in their first marriage is right there. The corresponding probability is 0.46. So if I define that as event A, probability that at least a family with at least one child younger than 18 years of age in 2013 had 2 married parents in their first age, then let's try this one more time. It doesn't work. Oh, well, so I'll just highlight it. So family with at least one child younger than 18 years of age in 2013 had two married parents in their first stage. So that is our event, the highlighted part. I'll call that event A. So probability of A is given in the problem, which is 0.46. So 0.46 corresponds to that particular level of two married parents in their first marriage. So we have 0.46. How would we interpret this? Interpretation: 46% of families with at least one child younger than 18 years of age in 2013 are or have two married parents in their first marriage. So we're just giving a probability to what are the chances that, you know, a family would have at least one child younger than 18 and that child has married parents in their first marriage. Part C, what is the probability that a randomly selected family with at least one child younger than 18 years of age in 2013 had two married parents? So I'll call family with at least one child the entire lengthy statement as event B. So probability of B, going back to our table, two married parents. If we have two married parents, I have two different cases. One is first marriage, and the two is one or both remarried. So I have that as well as that. Both cases have two married parents. So I have to add those probabilities because it doesn't matter if it's the first marriage or one or both remarried. So that probability is 0.46 plus 0.15, which is 0.61. How would we interpret this? So 61% of families with at least one child younger than 18 years of age in 2013 have two married parents. We don't care if it's the first marriage, it's one or both remarried, doesn't matter. Two married parents. And the first two levels with probability 0.46 and 0.15 corresponds to two married parents. So we have to add them together. So what is the probability that a randomly selected family with at least one child younger than 18 years of age had at least one parent at home? So this is one of those cases where the complementary rule plays a role. So probability So probability of at least one parent at home is the complement of no parents at home. So at least would be one or more, in this case only up to two, or else it'd be weird. The complement would be 0. So at least one and none are complements of each other. So using the complementary rule here is very effective. So if I define at least one parent as event D and no parent as the complement, I could use the complementary rule. I have information about no parent at home. So what is the probability of having no parents at home? That is 0.05. So that would give me 0.95. How would I interpret this? Oh. The interpretation would simply be 95% of families with at least one child younger than 18 years of age in 2019 have at least one parent in the family. So here we have a housing example which represents the number of rooms in a random sample of housing units in the United States. So they looked at 1 room, 2 rooms, 3, 4, all the way up to 8 or more. And this is the sample that they collected. This is the frequency distribution. And using this, we can find the probabilities for each case. So in part A, we want to find the probability that a randomly selected housing unit has 4 or more rooms. So to make things simple, I'm just going to define an event as number of rooms Four or more mathematically means probability x is greater than or equal to 4. So the number of rooms in the housing unit, which is x, is greater than or equal to 4. So all I have to do is add those values, 183 plus 230 plus 204 plus 123 plus 156 and divided by the total, which is 1,000. So 183, 383, 413, 630. Let me just see if my addition is correct. I don't want to put the wrong answer there. So we'll compute the total, which is 5 plus 11 plus 88 plus 183 plus 230 plus 204 plus 123 plus 156. That comes to 1,000. And greater than or equal to 4, 183 plus 230 plus 204 plus 123 plus 156, 896, and divide by 1,000. In terms of a decimal, that would simply be 0.896. Part B, we want to find the probability that the number of that a randomly selected housing unit has fewer than 8 rooms. So fewer means strictly less than, so X is less than 8. That is the same as saying X is less than or equal to 7. Now, one may say, well, I will just go ahead and add all the values, for 1 room, 2 rooms, 3 rooms, all the way up to 7 and get the answer. Nothing wrong with that. But if you use complementary rule, X less than 8 is the complement of X greater than or equal to 8. That event and that event are complements of each other. So I could write it as 1 minus the probability X greater than or equal to 8 means 8 or more rooms, which is 156 over 1,000. And you can simplify. And if you simplify, you would get the answer as 0.894, which is 894 over 1,000. So there is an 89.4% chance that a randomly selected housing unit will have fewer than 8 rooms. Part C, what is the probability that a randomly selected housing unit has from 4 to 6 rooms? So that would mean probability of 4 less than or equal to X less than or equal to 6. In other words, that equal indicates that we are including 4 and 6. How would we say it if they're not included? Typically, we would say it as between 4 and 6. That is a scenario where you don't include 4 and 6. Since the problem says from 4 to 6, it indicates that we have to include 4 and 6. What does it mean? That simply means probability that the number of rooms X is equal to 4, or X is equal to 5, or X is equal to 6. So 3 events, and they are connected by or. So we have to use addition rule. But the key thing here is that the events are disjoint. If a housing unit has exactly 4 rooms, we can't say that it also has exactly 5 rooms. If it has 5 rooms, we can't say it exactly has 6 rooms. So at any given time, only one of the 3 events, let me call it as A, B, and C could happen. So A, B, C are mutually exclusive. So we just add them together. Probability of X is equal to 4, plus the probability of X is equal to 5, plus the probability of X is equal to 6. So 183 plus 230 plus 204 divided by 1,000. And that would give us 0.617. Part D, what is the probability that a randomly selected housing unit has at least 2 rooms? So probability of X greater than or equal to 2 would mean the number of rooms in the housing unit is greater than or equal to 2. So again, based on what's given to us, we can, if we use the complementary rule, it would be easier to find the answer. What is the complement of greater than or equal to 2? It is X less than 2. Well, X less than 2 would simply mean there is only 1 room. Of course, you could say no rooms at all, but what is the point in having a housing unit if there aren't any rooms? So less than 2 would simply mean X is equal to 1 in this problem. And we have the frequency for that, that is 5. So 5 over 1,000. So that would give us 995 over 1,000. So it's 0.995.